Yoshua Bengio pointed out that consciousness is no longer a dirty word in cognitive neuroscience. It's clearly an evolutionary advantage for us to have consciousness, and Bengio says that we should have a formal definition of consciousness so that we can incorporate it as a prior in our machine learning algorithms.
First, have you ever questioned the nature of your reality?
No.
Bengio keynoted at this year's ICLR conference along with Yann LeCun, and today we are going to analyse his presentation.
Bengio takes on quite the challenge in this talk. He tries to connect elements from psychology and neuroscience, such as System 1, System 2 thinking, and the different areas of the brain, two things that we know from deep learning. And thereby, he formulates a theory of thinking and consciousness and what sort of role deep learning plays in the future of our push for artificial intelligence. I appreciate that he makes definitive statements here, and statements that leave him vulnerable to criticism by making very precise claims about consciousness, intelligence, and things like working memory attention.
In this talk, Yoshua Bengio presents a unifying view of topics to achieve better generalization in deep learning, and even get the magic out of consciousness. Bengio's talk from NeurIPS 2019, from System 1 deep learning to System 2 deep learning, brought ideas from Daniel Kahneman's Thinking Fast and Slow into the minds of machine learning scientists.
Yoshua Bengio was born in 1964 in Paris. He's one of the three godfathers of deep learning. He's a professor at the Department of Computer Science and Operations Research at the University of Montreal and scientific director of the Montreal Institute of Learning Algorithms. Bengio received his PhD from McGill University and was a postdoctoral fellow at MIT. He's one of the most cited computer scientists on the planet. In October 2016, Bengio co-founded Element AI, a Montreal-based artificial intelligence incubator that turns AI research into real-world business applications. Bengio was named an Officer of the Order of Canada. The same year, he was nominated Fellow of the Royal Society of Canada, and together with Geoffrey Hinton and Yann LeCun, Bengio won the 2018 Turing Award.
My collaborators and I are trying to understand the limitations of current AI, which is using machine learning, a lot of deep learning. We're very interested in the perspective of how agents like animals and humans who act in their environment actually have some understanding of their environment, understand the causal relationships in it, and how they can reason in it by doing things that current learning-based systems are not really yet good at, but that humans are very good at. The reason I got into AI when I was in my early 20s is because I thought that intelligence was one of the biggest mystery that science needed to understand.
Bengio cites Daniel Kahneman's dichotomous System 1 and System 2 modality of thinking. System 1 is the fast, intuitive, habitual and non-linguistic mode. We drive our cars and we recognize dogs using System 1. System 2 is our slow, logical, linguistic, conscious thinking mode, allowing us to plan and reason with explicit knowledge. Chomsky famously argued that language was externalized thought.
One general assumption about language, almost a dogma in philosophy, common understanding, linguistics, psychology, is that language is primarily a means of communication and that it evolved as a means of communication. Probably that's totally false. It seems that language is evolved and is designed as a mode of creating and interpreting thought. It's a system of thought, basically. It can be used to communicate. Everything people do can be used to communicate. You communicate by your hairstyle, style of walk, everything. And yes, language can be used to communicate, but it doesn't seem to be part of its design. Its design seems to be radically different, and in fact even seems to undermine communication. If you look carefully at the structure of language, you find case after case right at the core of language design where there are conflicts between what would be efficient for communication and what is efficient for the specific biological design of language.
One of the things I really liked about Bengio's presentation is that he asserted that a lot of implicit System 1 knowledge cannot be verbalized or explained. There's a lot of noise in the machine learning community at the moment about explainability. I like the idea that a lot of knowledge cannot be verbalized and therefore cannot be explained. I think the emphasis should be on model robustness and generalization and error testing. There are many things which we are competent at, yet we cannot verbalize or explain. Any attempt to do so, in my opinion, is mere confabulation. Anyone who's taken psychedelics before can attest to the ineffable conscious experience. Language itself appears to be part of our System 2 apparatus. Yannick disagreed with me on this. He thought that it was possible to verbalize System 1 activities. What fascinates me is that our language only covers the domain of our shared physical reality. This seems to contradict Chomsky's claim that thinking comes before externalized language.
Now, you said human. Do you think if those intelligent creatures are out there, do you think they experience their world?
They are evolved, if they are a product of natural evolution, as they would have to be, they will also experience their own world. So consciousness isn't just human, you're right, it's much wider. It may be spread across all of biology. The only thing that we have special is we can talk about it. Of course, not all people can talk about it.
One of the things I took issue with in Bengio's presentation was his assertion that consciousness is only a System 2 phenomenon. This appears to fly in the face of the wisdom of some of the experts in the field that claim that consciousness is merely experience and that it is experienced throughout the animal kingdom.
Experience. Consciousness is any experience. Some people call it subjective feeling, some people call it phenomenology, some people call it qualia if they're philosopher, but they all denote the same thing. It feels like something, in the famous word of the philosopher Thomas Nagel, it feels like something to be a bat, or to be an American, or to be angry, or to be sad, or to be in love, or to have pain. That is what experience is. Any possible experience. Could be as mundane as just sitting here in a chair. Could be as exalted as having a mystical moment in deep meditation. Those are just different forms of experiences.
In my opinion, we should steer the conversation away from consciousness and focus on intelligence itself, much like many people in the field, including Francois Chollet, are doing at the moment.
It's going to require consciousness, which is not things that would normally be required by an intelligent system. If you look at, we were mentioning earlier, like science as a superhuman problem-solving agent or system, it does not have consciousness, it doesn't have emotions. In general, so emotions, I see consciousness as being on the same spectrum as emotions. It is a component of the subjective experience that is meant very much to guide behavior generation, right? It's meant to guide your behavior. In general, human intelligence and animal intelligence has evolved for the purpose of behavior generation, right? Including in a social context. So that's why we actually need emotions. That's why we need consciousness. An artificial intelligence system developed in a different context may well never need them, may well never be conscious, like science. I think intelligence is essentially the efficiency with which you turn experience into generalizable programs. So what that means is it's the efficiency with which you turn a sampling of experience space into the ability to process a larger chunk of experience space.
This is what Cristof Koch said on the Lex Friedman podcast.
Unclear whether the intelligence we're engineering has anything to do with consciousness and whether it can experience anything. Because fundamentally, what's the difference? Intelligence is about function. Intelligence, no matter exactly how you define it, sort of adaptation to new environments, being able to learn and quickly understand the setup of this and what's going on and who are the actors and what's going to happen next. That's all about function. Consciousness is not about function. Consciousness is about being. It's in some sense much fundamental.
Consciousness is something that interests me, though. I've been meditating every day with Sam Harris's Waking Up app. One of the things he tries to do in his practice is to get you to conceptualize that the self is an illusion. He will ask you whether there is a locus of consciousness and whether you are behind your face. He will ask you to look at things in your visual field and to reason about whether there is a subject-object relationship between you and what you're looking at. Ultimately, he describes consciousness as being like an ocean. It has a surface, And thoughts that come into your head are a bit like waves on the surface of that ocean. He wants you to conceptualize yourself as being an executable program, self.exe, which runs in the operating system of your consciousness. Why am I telling you this? It goes to show that quite often we try to use language, we try to use analogies to describe what's going on in our conscious experience, but we're always reaching. We can never quite describe what's in our conscious experience because it's ineffable. It's ineffable because there is no language in our shared physical reality that we can develop to describe what we are experiencing. So Sam Harris goes on to explain in this following clip that consciousness is quite clearly system one. It just is what we are experiencing in this moment.
Okay, what we truly have is this moment and this. And we spend most of our lives forgetting this truth, repudiating it, fleeing it, overlooking it. And the horror is that we succeed. We manage to never really connect with the present moment and find fulfillment there because we are continually hoping to become happy in the future. And the future never arrives.
This presentation continues on this idea, and I'm really looking forward to discussing the general idea of System 1 and System 2 thinking, as well as how it relates to deep learning. Bengio ties in several areas of research at play to achieve systematic generalization, a particular kind of atom domain generalization whereby the test distribution is different from the training one but follows the same rules of semantic and syntactic composition. Bengio and his collaborators explored systematic generalization on the Clever dataset in a paper titled Closure. Closure tests how visual question answering systems learn to reason about the arrangement of objects in 3D space. An example of systematic generalization here is to go from answering questions such as the object that is the same size as the red cube to out of distribution questions like the cylinder to the left of the object that is the same size as the red cube. In their Closure paper, they find the most success with a vector representation variant of neural module networks, an interesting approach to routing different kinds of computation for different questions. I'm really looking forward to discussing these kinds of networks, as well as the topics of sparse factor graphs and causality, attention and consciousness, and how meta-learning across tasks and datasets fits into this picture.
I enjoyed this talk, and I hope you enjoy us coming to terms with what Bengio says. Even though I disagree on some of his claims, I had a lot of fun doing this, and I hope you have fun too. Cheers.
Remember to like, comment, and subscribe, and we will see you back next week.
Look at me, I am Casey Neistat.
Hey folks, and welcome back to the Machine Learning Street Talk YouTube channel with me, Tim Scarf, and my two compadres, Yannick Kilcher and Connor Shorten. It's been an incredibly exciting week for us, actually, because last week we did a reaction to Yann LeCun's keynote presentation at ICLR, and he retweeted us, and he also made a post on Facebook, and we've just been absolutely elated by that.
It's great. our view graph was like this, and as soon as he posted it shot up straight. It's fantastic.
So Yann, thank you very much for that. We really, really appreciate it. And he even made a post on his Twitter afterwards saying that it was really interesting for him just to see how guys like us could wrestle with the material in his presentation. And we got some things and some things we struggled with. And for someone at Yann's level, he can't even imagine what it would be like to, not be a wizard at deep learning. So I think it was really interesting for him as well.
Yeah, and to everyone that watched, of course. I mean, this means a lot to us. Ultimately, we're just rambling here, and figure out that people are actually interested in this is a big compliment to us.
Today, we're going to continue with the ICLR 2020 theme. Immediately after Yann LeCun's presentation, Yoshua Bengio, one of the other godfathers of deep learning, went on to do a really interesting presentation. And today, we just want to step through that as well, because we think it's really interesting. I think he did the same presentation at NeurIPS as well at the end of last year. So it's definitely something that Bengio has been putting a lot of thought into at the moment.
Yeah, I think there's so many interesting ideas with it. And I'm really interested in the idea of meta-learning, and particularly meta-learning in the context of saying, here are a bunch of tasks, the mutual information of all these tasks, like Google's recent metadata set, or things like the visual task adaptation benchmark. Like this idea that looking at different tasks can help us find these high-level features that help us generalize and form this kind of transfer to out-of-distribution error. And so another thing that I really thought was interesting is he's pretty particular with his language. He doesn't just say generalization, he says systematic generalization. So I think it's interesting, particularly in like Clojure, where they study the clever data set and what those models learn, is looking at the particular kind of ways we want these models to generalize, not just a random generalization test, but particularly trying to see if they can derive rules. Like one example from Clojure is in this clever data set, there's a bunch of these like objects in 3 dimensions, and you have to say things like the object that is the same size as the red cube, and the model would answer something like the orange triangle or whatever. So the idea of systematic generalization would be, can it then do the cylinder to the left of the object that is the same size as the red cube? So seeing if this particular kind of generalization. So I think that kind of being specific about that language is really interesting as well.
I want to touch on Francois Chollet's definition of intelligence as well. So in his paper on the measure of intelligence, he talks about developer-aware generalization and systemic generalization, and also 4 degrees of generalization. So it'd be really good to touch on that. It's really interesting to me to hear this talk of System 1 versus System 2. And I had always thought of System 2 as being referenced in the context of expert systems from the 1980s. And those things were very brittle, and they were the antithesis of generalization. But this is a little bit different. Bengio's talking about how these high-level concepts can be recombined in many different ways and will allow you to generalize to things that you've never seen before in training. So this is definitely something I'd like to explore as well.
Yeah, it's so interesting to me to take, like, let's be more specific about generalization and try to like exactly pick apart the different areas of generalization we're trying to test. It's not just about training it on a cat versus dog classifier and then seeing what it does with a bird, but like being more specific with how it generalizes.
I think we'll have to get into it. I mean, the talk flows really nicely, and I think Bengio explains what he means fairly well throughout the talk, and there's a lot of interesting stuff to pick up.
Hello, my name is Yoshua Bengio, and I'm going to tell you about future directions for deep learning, in particular about deep learning priors associated with conscious processing. So consciousness has been studied in neuroscience and cognitive neuroscience with a lot of progress in the last couple of decades. And I think it's time for machine learning to consider these advances and incorporate them in machine learning models. This can also be helpful for consciousness research by helping to formalize and test specific hypothesized functionalities of consciousness, help to get some of the magic out of consciousness, understand the evolutionary advantage of consciousness, the computational and statistical advantage. For example, I'll tell you about systematic generalization. And of course, provide these same advantages that we believe humans have to learning agents as well.
So I think one of the big things here is that he wants to remove the magic out of consciousness, and he wants to formalize it, and he wants to incorporate this formalized notion of consciousness into machine learning.
It's an absolutely giant task. Let's just take consciousness and put it into machine learning. Of course, there's so many unsolved things here, like what is consciousness? As he says, why is it here? And the evolutionary advantage. So basically, what the problem that consciousness was basically to solve. And maybe get a hint on that, we might be able to deduce how consciousness works or what it's for. He's going on to have a very specific model of consciousness. But I think the entry point is very good to say basically, okay, there's this thing called consciousness and we humans have it. And since we want to develop something like human level AGI, it might be useful for a machine learning system or for an AI to also have this consciousness property.
And he talks about the evolutionary advantage of consciousness in respect of systemic generalization. So he's saying that it has been a huge advantage, and that's why we have this cognitive ability to generalize.
Yeah, I mean, something we're going to get into later is definitely like, my thinking of it now is that like consciousness is enabled by attention over these like perception representations that deep learning has discovered already. So yeah, I mean, it's almost kind of like scary to think about, but I guess I'm willing to believe in the idea of like simulation theory a little bit, that the idea that it could be that everything is simulated. And I guess from this, I don't think that, I think that machines could be conscious after watching this.
Well, there's a couple of things there, because there's Nick Bostrom is this philosopher, and he had the argument from simulation. And it goes roughly along the lines of how many possible civilizations are there in the universe that develop a technical sophistication high enough to create a simulation of the universe. And he makes a reasonable argument that there are more than one. If there are more simulations than there are real universes, then it stands to reason that there's a pretty good chance that we are in a simulation ourselves.
My problems with that, because this is kind of predicated on the notion that then within the simulation, maybe the simulated ones would again simulate and so on. You get this explosion. Ultimately, the probability that you're in a simulated universe is close to 1. That's not really thought through. Probably there's like a physical limit to how much this recursion can go just by the nature of physics of the universe. And it feels better to think you're in the real world. So I just don't accept the argument.
That's super interesting. I think the thrust of the argument, though, is to serve as a mental thought experiment, that if you could reduce consciousness down to information processing, is that something that sits well with you or not?
Well, is the question whether your consciousness itself is simulated, or is it just like Matrix style that you're somewhere in a box and you're plugged into the simulation?
Well, that's really interesting as well. So one view is that if you were a materialist, you believe that your entire conscious self is physically contained inside your brain, and you're likely to think that it's achieved with information processing. Another conceptualization is that we are plugged into the matrix, or the actual processing nexus is in the cloud somehow. We're like thin clients and the processing happens somewhere else.
Yeah, but then at some point it makes no difference anymore whether you're in a simulation or not, right? If everything's just processing. And the other part is consciousness actually come in. Like if level 2 thinking is simply attention over these representations, that doesn't mean consciousness yet. Or like, is it saying, so basically, if I build a system that does attention over these high level concepts, is it conscious? I don't think so. Consciousness is somewhat the awareness of the thoughts about the thoughts itself. It's like this meta awareness of these thoughts, right? Thoughts about thoughts. And the question still in throughout Bengio's talk, basically for me, was always, where does exactly consciousness come in? Because he just defines consciousness as what he defines it as, but I don't see it the same way.
There was a wonderful quote in the Francois Chollet paper by René Descartes in 1637, and it was incredibly prescient for him to say this back then. He said, even though such machines might do some things as well as we do them, or perhaps even better, they would inevitably fail in others, which would reveal that they were acting not through understanding, but only from the disposition of their organs. So he said that in the 16th century, and he made the extremely astute observation that simply performing a task is not the same as understanding it, or even having the capability to learn it.
Well, imagine like such a complex task, and we already have the neural architecture for thoughts about thoughts. We have meta learning algorithms where we have the low level perception, the attention on the low level perception, and then we might even just put an attention over that. So it's not like we don't have an idea of the architecture that could think about thoughts. And so imagine this crazy complex environment, and then even an environment where like our own reward isn't clearly defined. Like we're constantly evaluating our own state of mind to see what reward are we really pursuing even. So it's like I imagine any kind of information processing system that has that fine grain that's trying to say, what is my reward? What is my environment? I have all this high dimensional stuff, and I'm constantly going through these levels of processing. I think it's totally possible that that's what consciousness arises from.
Absolutely.
I would agree with that. And let's contrast that to what we have now, because Connor sent this wonderful article. I've not actually read this, but it was by this chap called Cristof Koch.
Yeah.
And he was kind of asserting about intelligence, and he was talking about this causal power onto itself. So he said that the firing of neurons in the brain that cause other neurons to fire a bit later is one example. And this made me think, because if you look at a neural network now, it's basically a computer program. It's not intelligent at all. It's not like a normal computer program written with code. It's just a bunch of neurons in a network. But for all intents and purposes, it's a computer program. But the reflexivity seems to be the important bit. So if the program could trigger itself, if it could create this reflexive loop of computation, could that then develop into consciousness?
That's the argument I was making, actually. It's a difference between stacking attentions on top of one another and having the attention mechanism attending to itself. Right?
To understand this, let me talk about two kinds of systems that Daniel Kahneman described very clearly in his book, Thinking Fast and Slow. The System 1 tasks and System 2 tasks. So System 1 tasks, imagine you're driving in a known path, and you don't actually have to give all your attention to the driving. Somebody can talk to you and you can respond. System 2 tasks require your full attention, your full conscious attention. And if you're driving in a new place, that requires you to think, to plan, someone to talk to you at the same time. System 1 tasks involve intuitive knowledge. They can be executed quickly, unconsciously. They happen in one step in parallel in your brain. Usually they are hard to explain verbally, and they can be executed in a habitual way. They regard implicit knowledge, and this is where current deep learning is good. What we want to do is to extend deep learning to also handle System 2 tasks, which are executed slowly, sequentially, in a conscious way, can be described verbally for everything algorithmic involving reasoning or planning and explicit knowledge. One interesting property of System 2 tasks and conscious processing in general is that they allow to manipulate high-level semantic concepts, which can then be recombined combinatorially in novel situations. So there's a connection to out-of-distribution generalization, like in my driving example.
There's lots to pick apart there. The first thing I want to pick apart is the jargon. Now, quite often people in machine learning talk about semantic things. And what that means, in my opinion, is if you were Google or if you were the Bing team, you would want to build up a semantic view of the web. And semantic just means information that I'm interested in. So if you were building a dog classifier, the dog would be semantic. If you were Google and you were parsing web pages, then products and people would be semantic information.
I think there's another level to it. Like one of his paper, or I don't know if this is Bengio's paper actually, but he talks about neural module networks a lot that are looking at different ways to combine different types of operations. So like one common way is, let's say you're doing to classify whether I have a peace sign up or whatever gesture I'm doing. You might break that up into an object detection model, and then you might deploy the pose detection on my hand. So to me, one interpretation of System 2 and System 1 is System 2 is trying to combine these different tasks in the ways that make the problem more tractable.
System 1 tasks that combine other System 1 tasks, right? Because it basically says anything that's sort of
and this is a very human view, I think we talked about this last week, is that anything that for a human seems very, intuitive, fast, implicit, muscle memory, whatever. Now, contrary to what he says here, please don't talk while driving, even if it's a road I love the second stock photo, by the way, though. Stop, don't talk to me. Also, the System 1 is anything that's intuitive, and you can intuitively combine also neural modules. I think System 2 is more where you have to consciously think about it. The sequential is in red and the conscious is in bold. That's both means important, I think. And and the conscious is in caps as well. So makes it clear that you want the System 2 is anything where you sort of have to spend mental effort to come to a conclusion, whereas the System 1 almost happens like automatically, like you don't have to actually mental effort to achieve it.
One thing that really interests me is he talks about System 2 as being better for generalization. System 2 can mean symbolic approaches. And I liken that to in the 1980s when there were knowledge graphs. And the reason we stopped using those were they were very brittle and they did not generalize.
And how else can a machine hope to understand what's going on except through learning? If you're not learning, what else are you doing? Well, you're putting all the knowledge into the system. And that just feels like something which decades of AI have told us is maybe not a dead end, but certainly has a ceiling to the capabilities. It's known as the knowledge acquisition bottleneck, that the more you try to put into something, the more brittle the system becomes. And so you just have to have learning. You have to have learning. That's the only way you're going to be able to get a system which has sufficient knowledge in it, millions and millions of pieces of knowledge, billions, trillions, of a form that it can actually apply for itself and understand how those billions and trillions of pieces of knowledge can be leveraged in a way which will actually lead it towards its goal without conflict or other issues.
But now we're talking about System 2 and explicit verbalizable knowledge again in the setting that it can generalize. And Bengio goes on to talk about you can have recombinations of these System 2 semantic objects. The really interesting thing about System 2 is that the things that the semantic objects that you reason about can be verbalized. They tend to be words in the English language. And Noam Chomsky was famous for saying that language is a system of thought. When we speak to each other using language, it's kind of like externalized thought, which is really interesting. Because System 1 is also sequential. If you look at a neural network, it's, as we were saying last week, it's a sequence of manifold transformations. But the key thing is that it can't be verbalized or understood using our language concepts. And this is one of the reasons why I'm quite skeptical about explainability, because he's kind of implying that System 2 is explainable because we can verbalize it, and System 1 isn't explainable. I can't explain to you why I recognize a dog.
I was just going to say maybe it ties into embodiment a bit as well. The reason language is so explainable is because that's the purpose of it. Even though when I get up to make a coffee and I'm thinking in my own head, not communicating to anyone, I'm still thinking in language. I'm not thinking in some abstract space. What's like a good example of a System 2 System 2 thing, so we can have this clear, this is System 1, this is System 2. So to me, the thing is hierarchical reinforcement learning, where you're designing a plan is the System 2 level, and then System 1 is the execution of the plan. Do you think that's the best example of this to paint this picture?
That is a very, very good example, though we have to be a bit careful with something like search, because I'm especially path planning. I'm always so amazed by like my human ability to path plan. When you're like running on a bit of a dirt path and all of a sudden a bunch of puddle are in front of you, right? And the speed with which you plan your way through these puddles, where your steps are going to go, is absolutely staggering to me. Like every time I consciously experience this and I watch myself plan my path through something like this is crazy. And this is still System 1. Like my ability to approximately path find something is still, so not all of like search is System 2 tasks, even though we can't do it with deep learning yet. But the analogy is very good. Like if I want to achieve a goal and that I don't know how to do, I have to spend mental effort to make a plan until I break it down to the pieces that I know, right? And then that is just autopilot.
Yeah, well, search like becomes system one through experience, right? Like even in our, like, to go first to our AutoML things, we have these like where you can predict the performance of a program based on its like genotype. So like a large scale evolution of image classifiers, we have this like genotype that defines rendering and classifier. If you search through like 80,000 of those, you'll start to be able to predict performance from the genotype itself. It's like when I see someone on like a skateboard riding through campus, I'm like, this guy's going to crash into somebody, because I imagine myself riding a skateboard through campus, I'd freaking crash into everybody. But so as the experience accumulates, the search problem of navigating becomes so much easier.
Loads of people have said to me recently that reinforcement learning is system two. I was speaking to a guy who runs a reinforcement learning company in Europe, actually. Let me share my screen to show you the anecdote that he gave me. Basically, I called bullshit to the guy. I said, look, you're talking about reinforcement learning. I think it's still system one, because I've just watched Bengio's talk. And even before we show this, it might be instructive to show this wonderful YouTube video that Connor sent earlier about chimps. So this is system one. And this video basically shows a bunch of chimps apparently have better working memory than us. You can mask the numbers and they remember where the numbers are, and they can press them in sequence in order to get a peanut. And on one instance, the monkey got distracted for about 30 seconds and then turned the monkey's attention back to the screen and still managed to remember. It's incredible what monkeys can achieve. And this chap, Harry, he came back to me and he talked about this experimental setup. So he said, one setup, there's a hidden classification rule and a deck of cards which have some kind of figures on them. The test subject picks cards one by one and is forced to classify them into one or two classes. There's feedback about correct and incorrect choices after each card. In some cases, the test subjects never become aware of the hidden rule, but gradually learn to make better and better choices. Sometimes, typically when the hidden rule is relatively simple and depends on just one input feature like the color or the shape of a figure, the test subject becomes aware of the rule and the classification performance abruptly jumps to 100%. This kind of eureka moment is rarely seen in monkeys doing the same task. They have virtually the same performance as humans as long as the task remains a big data system one learning task. But humans perform at an entirely different level if they manage to engage system two cognition. So if you see this rapid jump, what it means is that human beings can somehow turn it into one of these consciousness priors and reason about it in some level of abstraction that's above system one.
Analogy with the rules, it might be a good one, but I don't think it's in general that monkeys cannot do that. I think there's enough examples in the animal kingdom where exactly this type of thing is happening, where there's like a snap moment, like, that's how you do it. And then not only that, but then other monkeys watch these monkeys and can like instantly transfer learn. The only difference here is they probably can't communicate their solution through language.
Well, this is something that Chollet talks about in his ARC benchmark and dataset, because the problem with so many intelligence tests is that it's possible to learn shortcuts.
Yeah, absolutely. The notion that RL is a system 2 task, I have not seen an RL system that gets the eureka, that like discovers the rule. RL is the exact opposite. Like it will just brute force around until the reward gets good, and then it will just repeat whatever.
Well, that's super interesting, though. A eureka moment would be noticeable on the training convergence behavior. And something Bengio talks about later in this talk is this notion of you can determine causality between variables based on the speed of learning. And exactly that. In a reinforcement learning algorithm, the convergence is exactly the same. So does that not indicate that there's no system 2?
Not necessarily, because it's not only the convergent. That you see that in RL systems. Like as soon as they like figure out a path that leads to good reward, they can like the performance can jump very quickly. But that doesn't mean they've learned the rule. You'd have to explicitly measure on a new task that is different, but the rule remains constant. And that's where really we get into what Bengio's going to say later. He's basically going to talk about what if you have these high level concepts and you have to learn how they connect to each other, and that enables you to generalize to a different set of high level objects, but that connect in the same way, right? And that's really what we don't see from any machine learning so far. And the idea of building these knowledge graphs was actually very smart, because clearly this is going on in humans. Clearly we reason about these entities, but the brittleness that you have to pinpoint the exact entity you're talking about in the AI system was just devastating. So now that we can maybe solve this brittleness, we can come back to that.
On the side of the eureka moment idea, is we discuss in Chollet's intelligence paper this analogy of uncrumpling a piece of paper. Don't you think the eureka moment is just like you're transforming the data manifold as you go from ridiculously high complex, the true visual data manifold, into these compressed data manifolds? Don't you think it's like uncrumple? It's like, oh, I got it. Now the points are separated.
A eureka moment would be if you could uncrumble a new piece of paper in one step, right? Like, when you've discovered how to do this, I'll give you a different one, and you can just be like, snap. That's how it, like, the difference between learning to kind of solve a Rubik's Cube by getting better and like more and more to what you want, to me telling you, here's the rules.
So I think an interesting idea you're getting at is, so I've learned to uncrumple this one cat image. I've uncrumpled it at, say, layer like 8 is now when my cat image can be classified as a cat. So is the idea that now the next time I get a cat image, I don't have to go through 8 rounds of uncrumpling. Now I can just uncrumple on the first layer. Is that the idea?
It's more like the next idea, you get a data set where 2 things are different. Well, maybe that's too much different, but it's like the generalization across these categories.
Something that Harry said was that system 2 is slow to think but fast to learn. Now, I think that that's something that we should linger on for a second. In the example Connor just gave, at first it takes a long time to recognize this cat, but if there were a system 2 of consciousness, it's almost like there would be a kind of shortcut after that initial recognition.
Yes.
Maybe what happens is you need a lot of capacity to learn how to uncrumple it at layer 8, and then you do like knowledge distillation, some fast network, mobile net, say you can have some faster forward pass network. And so it uses the big network and then it puts it into that. And now you're like, cat, 2 seconds compared to 20 seconds or whatever.
That's really interesting. Maybe that happened. Maybe our intelligence produces skill programs, and when a program works, the brain then works on a higher level of abstraction, executing those skill programs.
That's like saying that the act of learning itself is a system 2 program. The question is, are there other system 2 programs except from learning? I mean, I don't know, but I think Bengio's going to make that claim here, that there are other system 2 tasks than learning, for example, planning.
Knowledge that we have in our brain about the world can be more or less separated into 2 kinds: the implicit knowledge and the verbalizable knowledge. And my main message is that verbalizable knowledge is a special kind of knowledge that satisfies some assumptions that we should try to cover and describe so we can put them in machine learning architectures and training frameworks. So this knowledge is organized around concepts that we can name with language. And so there's a strong connection between that research and building better natural language understanding, for example. And the priors could extend deep learning to incorporate the kind of structure that exists for these high-level concepts.
Just came to mind because he says basically system 2 is what you can verbalize. But sometimes I'm verbalizing system 1 things. Like if I have to explain to someone how to shoot a basketball, right? This is very intuitive to me, but then I can sort of introspect and talk about what I'm doing in order to transmit this to the other person. So this would put more weight on this hypothesis that maybe all System 2 is learning and distilling things into System 1 things. And then I can transfer my System 1 knowledge to someone via System 2.
Are there any System 1 activities which are not physical, that are entirely in your brain, that you could verbalize? Because I think his point was the reason they're not verbalizable is when you describe how you shoot a basketball, it's a real world concept. So there's a whole language and vernacular you have to describe the physical movements. When you recognize a dog, you wouldn't be able to explain to me how you do that.
Well, yeah. I mean, attempt. I can say, look, it has these ears and so on. And I can be very specific about the things. I can even describe sort of pixel patterns. I can't describe it fully, but I can still make language claims about my System 1 knowledge.
But I think you would be making it up if you did. And the humans have this tendency, because we have this cognitive dissonance, that we like to delude ourselves that we understand the way our brains work. And quite often when you ask humans to recount why they did something, they'll confabulate and they'll basically make it up.
I can't teach someone how to throw a basketball, right? How do you explain that?
Indeed, you can. And because the physicality of it is verbalizable,
okay,
you can turn that into a program and can transmit it with language. It can be received by another person. They can execute the program, and then their System 1 brain will learn it indirectly.
Yeah, maybe here the idea is like we only have kind of System 1, and then System 2 comes from like our communication with each other. And it's like maybe without, if you were like a human, just one in the world, you maybe wouldn't have System 2 at all, because you never would need to verbalize it. But then you maybe also wouldn't be as smart, because we verbalize our knowledge even in our own mind. We like make notes and write things down to distill it within ourselves. So maybe consciousness is a shared thing. We all are System 1 things, and now we all share this System 2 consciousness. It's the whole language itself is our shared consciousness.
Well, that's interesting as well, because language is externalized. And Chollet talks about this as well, that there are many types of intelligence in the real world. Some of it we don't recognize as being intelligence, like evolution. Natural evolution is a wonderful form of intelligence, and it's open-ended and it's very adaptable and so on. So there is a form of intelligence which is externalized.
That then bends the definition of intelligence a bit. I mean, if you say evolution is intelligence,
well, why not?
Well, it just depends on what you mean by intelligence. And okay, he says there are many different kinds of intelligence, but I can say that as well, and just redefine intelligence until the thing I want to be intelligent fits in that. Like the book is intelligent because it contains many smart things.
Well, I love Chollet's conception. So he says that intelligence is the efficiency in which a learning system turns experience and priors into skill at previously unknown tasks.
That evolution is terrible at that.
You mean it's inefficient?
Absolutely.
But what's great about evolution, though, is its adaptability. Because Chollet has this thing, he says that in the 1970s, we thought that when we solved chess, when we could make a chess program, that would be intelligent, because to play chess, you need to have reasoning and planning and so on. And basically, it was a brute force search algorithm. Now we've done the same thing with reinforcement learning, but we've done a brute force learn algorithm. So we just have millions and millions of iterations. And Chollet is saying skill is easy. You can buy skill with unlimited priors and experience. You can just throw loads of training data at it. And that's why any measure of intelligence needs to be looking at things like the efficiency of acquiring new tasks. Garry Kasparov is intelligent, not because he has a skill, but because he had the capability, the capacity to learn and acquire that skill. And that skill is something that generalizes. If you look at most of these reinforcement learning approaches from DeepMind or from OpenAI, the Dota thing, they have almost no flexibility. They're completely locked to a specific customization of the game. I think on the Go algorithm from DeepMind, if you even increase the board size, then the algorithm would need to be retrained from scratch. It has no generalization power whatsoever.
Well, so with the humans. Evolution has taken about 1 billion years to come up with something that can barely play chess. And the Deep Blue algorithm, it can generalize to a new chess game with no expenditure at all. Okay, if you change the rules, but then you have to retrain the humans as well.
Well, this is interesting as well, because I want to get into this, because I would call the Deep Blue chess algorithm an expert system. It's algorithmic. And by definition, it has no generalization power. But actually it does. It has generalization power in the same way a sorting algorithm does. A sorting algorithm can generalize to any permutation of numbers, but it's not learning an abstract representation.
But it can verbalize anything it's doing, right? Deep Blue will tell you exactly, I'm doing this move because Deep Blue is basically a tree search over a mixture of handcrafted features. So it can tell you always like, oh, this handcrafted material is very good in this path, right? And it can verbalize pretty much perfectly what it's doing.
But it's a program.
Yes.
So this is a diagram from Chollet's paper, and I thought this was really interesting. So we're asserting that there's a difference between intelligence itself and a skill program. So in his conception of intelligence, these skill programs can be generated dynamically. And he would argue that on the latest DeepMind AlphaGo or AlphaZero system, that was just a skill program. So it's a static program, and it has no intelligence whatsoever. It was created from an intelligent system. And he would argue that that intelligent system was the creators of the reinforcement learning algorithm.
Well, for the sake of our focus on consciousness, could the skill program have consciousness as well?
Or another way of asking it is the intelligent system also a skill program?
It doesn't have to be, right? If the skill program is a human and the intelligent system is evolution conscious, I think it's rather disconnected from consciousness is disconnected from this.
Is the consciousness or the intelligent system maybe could be like our collective consciousness through language, and then we interface with the collective consciousness for our own system one. Maybe we only really would have that.
It's true. I mean, other species can communicate, right, through language, but they have sort of a proto-language. And of course, let's assume, I don't know if they are conscious or not because of that, but you can certainly think of communication without consciousness. That's certainly something that's possible, because communication basically is just a transmission of information, and you can do that without being conscious, right? And you can be apparently intelligent without being conscious. So if intelligence is just this ability to generalize to new tasks, to produce these skill programs, you don't have to be conscious for that. But consciousness requires this kind of introspection ability about the consciousness itself. And it's also not clear that a conscious system necessarily has to be intelligent.
Why do we need consciousness? Why don't we just throw it away? Because it seems to me that Bengio is implying that we need system 2 and we need consciousness in order to improve intelligence. And I think that's bollocks. I mean, look at so many other examples of intelligence, like evolution, that are clearly not conscious.
Well, yes, maybe. Well, the question is,
why do we need
is evolution intelligent at the same quality and quantity of intelligence as we want AI to achieve? And the answer is probably no. We want AI to achieve a sort of intelligence like humans. And the only way that has ever happened is with consciousness. So I think the motivation here is purely phenomenological, is that you say, the only thing we know that works has this consciousness thing, so we might as well try to build this into the AI.
From the natural selection evolution perspective, obviously the better that you can attend over your own problem solving thing and the better sense you have of yourself, the better you're going to be at surviving. So just from that lens, I mean, the evolutionary advantage of consciousness or like introspection is that you get to like optimize your own problem solving mechanism.
What we are talking about, though, is the anthropocentric conception of intelligence. And Chollet argues that that's a good thing. And he says that at the end of Yann LeCun's talk, he says that there's no such thing as artificial general intelligence. All intelligence is specialized, and human intelligence is very specialized. I mean, Chollet gives examples of we're surprisingly good at doing things like the traveling salesman problem on a small number of cities. But if you flip that on its head and you do the opposite, which is to find the longest path, suddenly humans are really bad at that. We're good at solving spatial problems in 3D, but we can't do them in 4D. So we think of our own intelligence as being incredibly general, but it's not. We shouldn't delude ourselves. The domain of adaptivity is very, very truncated to the kind of problems that we might encounter.
And if you define system 2 tasks as anything where you have to expend mental effort, that is, I mean, it's a clearly human-centric way of looking at the world. But I'm fine with that as well, because after all, it's a practical solution, right?
Well, okay, let's say like mammal, where you do like gradient through gradient. So you have like the gradient of the inner loop and then the gradient of the outer loop. Do you think those two things become so intertwined that that could be where consciousness comes out of? With like sufficient capacity and a complex task and complex representations, like, because they start to become entangled. But again, I totally agree that like intelligence doesn't need to have consciousness.
I really don't like this false dichotomy of system 1 and system 2. What we seem to agree on is that system 2 allows us to take shortcuts. And because we have the mental apparatus in our brains, it means that shortcuts are appropriate in certain circumstances. Why could we not replicate that in a neural network? Is it just because they don't have the architecture or mechanics to take those shortcuts? Because there are loads of shortcuts on System 1 deep learning models. That's why it's so difficult to create a benchmark of artificial intelligence, because there are so many shortcuts you can take, especially if you have a fairly fixed task that you're performing.
A recent paper is like early exiting in BERT question answering systems, where they get to like layer 4 of the BERT model and they're like, oh, our confidence is high enough, we're not even going to go through layers 5 through 8, so we're just going to exit and predict earlier. Do you mean that sense that like we can predict quicker and distill how quickly we're confident about our prediction and exit our like processing of what we're going to predict?
If I mean, a system 2 system would be able to come up with that idea by itself. Right? Because right now the humans go and say, well, I need a new research paper, and why don't I just do this thing? And then, but so the human here is the system 2 thing that comes up with the idea of doing this at layer 4, right? I think, Tim, you said it very well. The fact that there are shortcuts in any individual task is different from what we actually want. What we actually want is, we can't really describe it, but it's something with generalization. It's something with, if I give you something new, you should be able to find the shortcut as fast as possible.
Exactly. I just want to quickly touch on something else as well. So in industry, people are always talking about explainability. And something I really like about Bengio is he's made it clear that a lot of knowledge cannot be verbalized. And that one-liner, I think, is beautiful, because as Yannick was saying the other week, explainability methods are a bit like reading tea leaves. And one of the things I'm interested in is I believe that machine learning is the next generation of software engineering. I'll hold my hand up and I'll say it's not intelligence. These are programs. They're skill programs. Some of them are written using code. These new machine learning skill programs are generated from data, and we don't understand how they work, but they are programs nonetheless. But these things need to be put into production. And there's a lot of people saying we need to understand their behavior. But why don't we just test? There are gradations, right? So the data scientists, when they're creating the model, maybe they should do some interactive explainability stuff just to check that it's not doing something perverse. So if you're detecting, I don't know, lions or something, you should make sure that you're not looking at where the grass is, you're looking at where the lion is. But once this becomes an engineering pipeline, you should be testing. You should be doing data grouping and semantic counterfactual examples, and you're doing things that can be automated. These explainability methods are the elephant in the room here is that deep learning models do not generalize. They only have local minimal generalization that depend on having a dense sampling in the input space. So they only generalize insofar as they interpolate between a dense sampling of training.
Well, I think it ties back to this idea of systemic generalization, and then particularly taking apart the kinds of generalization that we're interested in. So one paper squinting at visual question answering models, it says the question is the banana ripe enough to eat? So this systemic generalization is about the compositionality of that question. Can it also answer, are the bananas mostly green or yellow? So it's like, I agree, like these tests of explainability, I think it should be tests on like treating it like a black box, or not a black box, but like what kind of generalization are we after exactly, I think is important with that.
Yeah, that's a great example. So I think that I would call those logical consistency rules. And so they are great ways to test the robustness of the model, because we need to accept that these models do not generalize. That's the whole point. They do not generalize. And that's why we need to have some kind of mixture of symbolic and deep learning models. And we need to have a rigorous testing procedure.
Can we agree that if I build a explainable model and it can tell me in language why it made a certain classification, which is like the holy grail of the explainability crowd, it's still not system 2.
I think it does. That's what's so beautiful about what Bengio says. Some knowledge is not verbalizable.
Yeah, I'm not sure.
Let's play with it a bit. Why are you not sure?
I think if you give me time, I can verbalize pretty much any of my subconscious knowledge.
Wow, I think I disagree.
You verbalize why, and you say, nah, I can't.
Imagine your brain was actually 10 times bigger than it was. At what point would you stop saying that you can verbalize what's going on?
I also think you're not taking into account how fine-grained this subconscious knowledge is. Like say, to shoot a basketball, apply exactly 18 newtons of force in your tricep, like the exact force. And like how to see a cat would be like, do this exact thing in your brain. Like
but
I think
could. That's ultimately Alan Turing's contribution to say, look, any sort of function can be computed with a band described in a series of bits, right? With a bit string. And if what I'm doing is computing a function, I can describe it with a bit string and therefore with language.
Okay, yeah. Okay, so then maybe the question is, searching for that bit string is going to be intractable, though.
Absolutely. I'm not saying that, but I am taking issue with the fact that the system 2, system 1 distinction can be made with verbalizability. What maybe you can say is that system 2 knowledge is one where I have to verbalize, right? System 1 knowledge is I can just let it run. If I want to, I don't have to verbalize it, but I can.
Yeah, I struggle with that because I think there are many things which are ineffable. I mean, hypothetically speaking, if you were to take some psychedelic and you experience things where there were no human words to explain what you are, I mean, it's just a hypothetical.
Of course.
But there are so many examples of things that exist outside of our domain of understanding. Because inside our domain of common understanding, we place anchors, and those anchors are words. What about all of the things that are outside of that domain of understanding?
Well, I can just describe with words. If there's no word, I can use other words to describe the thing. Like there's a beautiful paper just came out yesterday, or like a GitHub project where someone trained GPT-2 on a dictionary, and it can make up new words, and it can make up, like, explain. I can be like a mathematician. I just define the new word and explain with using other words what the new word means, and then I'm good to go.
Yeah, do you think that'll be a good tool for like I saw like the Mina chatbot made that joke where the horse went to Hayvard, right? That was like this joke that the byte pair encoding had learned to put hay and verd together and make this joke that a horse goes to Hayvard instead of Harvard. Do you think that this word does not exist, kind of dictionary of made up words, could be a way for explainability with different segments of the word embeddings?
Nice question. Yeah.
Let's play with this. It makes sense. This person does not exist. So you take a whole space of known people and you can interpolate between them and create people that don't exist anymore. But the whole point of language is to provide reference points, semantically relevant reference points to our shared understanding of our reality. I don't think the analogy works. It doesn't mean anything to invent a word.
But anything that I would describe, any system knowledge that I would have would be part of our reality, and therefore, at least within the convex hull of the words that we have.
That would mean that the meaning itself would also be some kind of interpolation between the words that you use to create the new word. So you haven't really created anything new semantically.
But it's just because we don't have a word to describe something, as long as it's in the convex hull of other words, I can either use these other words to describe it, or I can just make up a new word and define it and then use that. So just because we don't have a word to describe something doesn't mean we cannot verbalize it.
That's true, but there is a space of concepts in reality that map to the convex hull of words that we know. And you're still not getting any closer to describing things outside of that convex hull.
But you first have to show me that the system one knowledge is outside of that convex hull, which I don't believe, because it's part of our reality. So we ought to have words for it.
Well, on the topic of is this explainable, like one example, so David Ha played with it, and then he goes by the Twitter handle Hard Maru, right? And the word came up with the definition for this is an intense heat, especially as caused by burning is how it talks. But like that doesn't make Hard Maru an intense heat. That's not explainable. So where does the interpolation come even? It's not like you can tell with this tool specifically.
Yeah, no, I mean, but if I define that word, right, if I want to transmit that information, I could define that word as the intense heat. It doesn't mean we have to come to the same conclusion, but if I define it and then we both accept that definition, we can communicate with it. I mean, I'm just not buying the you can't verbalize system one things.
I like the idea of you have to, is that the distinction is that you have to verbalize it. But that kind of goes back to embodiment and that in the say that all this multi-agent system. So that's kind of my idea that consciousness or system two is a product of all of us together.
Yes.
That's the only system. But then you also use it internally because we think in language too.
Yeah. So another inconsistency with this is the example that Bengio makes is system 2 knowledge can become system 1 knowledge, right? If I repeat a task that I have to spend mental effort on over and over again, it becomes system 1 knowledge. That doesn't mean I suddenly cannot verbalize it anymore just because it became a system 1 task.
We say that it's AI if we don't understand it yet. And again, you're going to get pissed off with me constantly citing Chollet, but I love him. There's something he talked about in his paper called the macaw duck. There's a guy called macaw duck, and he had this thing called the AI effect, where the goalposts move every time progress in AI is made. So every time someone figures out how to do something like make a computer play checkers, there'll be a chorus of critics that say that's not thinking. So as soon as we understand what it is, then it's not thinking anymore. And I would say it's the same thing for System 2. System 2 is like the bit that we don't understand, so we're calling it System 2. When we actually make that step, and I don't think it's any different to what we're doing now, then it won't be System 2 anymore. It will just be the same as everything else.
Well, the fault is with the people that claimed it was thinking in the first place, right? The fault is with the people that said, once we solve checkers, we have something intelligent. Like, no. It's like the fault clearly lies there. That's at least I think so. I would not know of a task even where I said once we've solved that, we have built something intelligent.
What kind of priors could help extend deep learning, incorporate the kind of structure that exists for these high-level concepts and System 2 tasks? So one of the first priors that I'll talk about in my presentation is regarding the structure of the joint distribution between those level, let's call them semantic variables. The joint distribution can be described by a graphical model, in particular a factor graph, which is sparse, meaning that the pieces of knowledge each involve very few variables. In addition, those variables often have something to do with causality. They're about agents, they're about intentions or actions, and they're about controllable objects. Another hypothesis that I almost already gave you earlier is that there's a simple relationship between those high-level variables and words or phrases. So there's a simple relationship between conscious thoughts and words and sentences in general. We can express our conscious thoughts. One assumption that I won't have time to talk a lot about, but is very clear, for example, in programming or in logical thinking, is that those pieces of knowledge can be reused. Think of them as rules that can be applied across many instances, which you can think of as like arguments of functions. And because of this system 2 computation can deal with variables and indirection. Very important point about that in variables is how it changes over time, how the distribution changes over time. And tell you later about those distributional changes, which we're going to assume are due to causal interventions. And because of this, they involve local change in the structure of the joint distribution. Maybe just one variable has changed or one condition has changed. And that only works because those variables have a causal semantic. So it's connected to this earlier prior that I mentioned. In addition, when there's a change in distribution, most of the rest of the joint distribution doesn't change, as well as the relationship between our observations, sensory data, low-level actions, and the high-level variables. So the only thing that changes when there's an intervention is some property or some values of high-level variables, but not their relationship to perception. Finally, another assumption that I won't have time to talk much about is about how we reason and plan and do credit assignment with respect to these variables. So the assumption here is that credit assignment only involves short causal change at each, and we do such a credit assignment.
So these shared rules, tuples, I assume he means a little bit like knowledge graphs again, where we have a subject, a predicate, and an object, and those rules can be shared across multiple instances. Are those rules learned? Are they fixed? Are they static?
That's a good question. Probably a mix between pre-programmed by evolution and learned by yourself, because then he talks about credit assignment, right? And that's mainly the learning part. So what he's talking about is he thinks that you have these system 1 systems that put whatever is input into this sparse factor graph. And the sparse factor graph, basically it has nodes that represent variables. So a variable could be my house, a ball, a job, my future, this piece of wood, but also more abstract things. And these nodes are connected by so-called factors, and the factors just specify how the nodes relate to each other. And I think later he gives the example, if I drop the ball, it will fall to the ground. So this very simple rule connects these factors. And says that system 2 operates in this space of these abstract concepts that somehow are sparsely connected to each other with these rules.
And how do you go from, let's say we have an image, you need to get the semantic information out of it. It might have a dog in it, it might have a tennis ball in it. Does that just mean that we have a neural network object detector to pull the semantic information out before it goes into this sparse factor graph.
Yes. That's basically what he's saying, is that you basically have an encoder. I think that's even a slide that comes up. You have an encoder that you can think of much like whatever your ImageNet ResNet 50, and you just put all that's coming in through your eyes. You put that through the encoder, and then you have the high-level representation. And the high-level representation, now this is your concept variable. So there you'll see dog. And now your consciousness basically operates only in the space of dog and doesn't operate in the space of pixels.
The only problem with this is back in the days of factor graphs and probabilistic graphical models, the graph itself was handcrafted by a human. So the human will say there's this latent variable, this represents a dog. Geoffrey Hinton, when he was talking about capsule networks, it was the ability to learn semantic information in a way that could be, invariant to different transformation of the image. But what I would like to see is some way of being able to understand what the semantically relevant information is without having to hand code it.
Yeah, the crux of the method here is going to be this sparsity, because we so far only know how to learn things that are fully connected. In our machines, we don't know yet which of these variables connect to which other variables, right? So what we do is we do whatever your soft attention, we connect everything to everything and then assign high or low weights. And what he's talking about is this sparse factor graph. It only will ever work if this is sparse. And we don't know how to learn sparse things.
Well, what do you think about like when you have the generator model that goes from the randomly sampled Z's into generated images? Then you can start to label the images. So it's like a supervised learning way of disentangling the representations from the Z space. So we're taking all these generated images and we're going to label them now. We're going to say these are the images where the face image, the guy has glasses on. So start to cluster the Z, find all the Z's that produce glasses, and we'll label them for you. So now what I think you can do, you keep doing that, glasses, hat, beard, all these little features. And now you have them in the Z space. You know which areas of the Z space are causing these different factors. So maybe now you could come up with an interpolation of the Z concepts easier. You have this kind of graph of this, there's overlap probably in the Z's too. It's not so, here's this node that is all the face vectors and they're so different from the hat vectors, they're not that, isolated from each other. So do you think that kind of supervised learning of to try to figure out which Z's produce which images, is that kind of a close idea to this factor graph thing?
So you're talking about GANs, right? So where you go from like a latent vector into let's say pixel space in terms of images, and then you classify that pixel space. Your hypothesis here would be that this encoder thing that maps the low level to the high level representation actually comes about by us having an internal generative model of the world. Because that's basically my translation of what you're saying, is that what we do internally is we say, okay, face with glasses with hat, that looks about like this. And then because we can do that, we can then again map it back to this high level space. That isn't entirely possible. That is a hypothesis. We don't know if our processing comes from generative modeling the data or purely discriminative modeling. But the generative model hypothesis would explain, for example, why you're so good at recognizing out of distribution samples. Because with a generative model, you get that for free. You can simply say, this data point, it doesn't fit into any of my classes, right? Into any of my data. Whereas if you were just a discriminative machine, you would not do that. And the second thing you say is also super, super important. And I actually agree with you in that Bengio says is there are these nodes. So it says this latent space is more or less a discrete space, right? So you have dog here, and you maybe have fur, and fur is somehow connected to dog, but it's still, it's entities. This is a hypothesis. The other hypothesis would be, look, this is all continuous. This is all a continuous space of things, and you can't really map this to these to these single variables. It's very interesting. I don't know.
I mean, just from the perspective of trying to disentangle factors, I think that the generative model is at least the best way to interpret it and make progress on it. Because we get to look at it and understand it.
So are you suggesting, Yannick, that our conception of reality, the way we perceive that we live in, is one big hallucination?
Maybe that's how you learn it, right? Maybe the way you learn high-level representation is just by trying to reconstruct reality from your brain, right? So that means you come up with a hypothesis of the latent variable, and then you reconstruct, and if it fits, right, then you know, this is the correct high-level representation. This is a completely different hypothesis from saying something like, you have a forward function, a classifier that just takes pixels and gives you high-level representation. It's completely different. Because with one, your ability to do that comes from your ability to generate, right? And that's something like that Hinton would say. Hinton is basically saying, what we're doing when we do object recognition is we do an inverse render, right? We align our latent model of the world with what we're seeing. But Bengio leaves this away. Bengio just says you have some sort of encoder that gives you this high-level representation. But maybe we can connect the notion of continuity that you said with these variables, but it's very hard. What you somehow have to say is that, it's very hard. I'm trying to connect the fact that these latent spaces appear to be continuous, but Bengio says something about sparse, discrete objects. And that doesn't really ring to me, except maybe if your discrete space is super high dimensional and every entry is a probability for one of these factors. But I don't see that. Generally, the high-level representation is not super high dimensional. So, and then he says it's sparse, which means that if now I imagine I have a small dimensional vector and that somehow represents those variables, if they're sparse, that means they must be independent. So now I have too few dimensions to represent all these variables. So either it can't be sparse, or it can't be discrete, or it can't be continuous in the way that we perceive the world.
Well, with the vector quantized variational autoencoder that powers like the OpenAI jukebox, they have the discrete code book, and then they're sparse based on the hierarchy. They share this discrete code at the top, and then as they go down the hierarchy of discrete codes at each level of the hierarchy, like this is sparse compared to this, like going down the tree.
Okay.
So that could be an example of a discrete latent code. I don't think anyone has done a discrete latent GAN, but I could see it working in the same way.
Maybe the question is whether or not that will lead to a sparse factor graph over these code book entries, right? Even though now it's discrete, but we still have a neural network that basically connects every entry in the code book to every other entry, right? The complexity arises from us being able to connect everything with everything, whereas Bengio says, no, it's sparse. We only should ever should come up with rules that connect 2 or 3 of those things. And I don't think that we know how to do that yet.
Well, he hasn't given us any indication on how this sparse factor graph comes into existence. It's just a conception. And the other thing that concerned me a little bit when you were talking about the human brain, it's very dangerous, this kind of anthropomorphization of deep learning concepts, because you were talking about a representation. What does that even mean for the human brain? Do we need representations? These signals just go to the relevant parts of the brain, and they just activate the regions. Do we need to have a compressed representation in the same way as a deep learning model? Does it even make sense to make that?
Well, the neuron firing pattern is then essentially a representation, right? So the neuron firing pattern, and that is certainly lower dimensional than the number of concepts you can express. That's what I mean. So I can describe your neuron firing pattern with fewer numbers than the number of concepts you could think of, because the number of concepts you can think of is addressed combinatorically by mixing different neurons.
But I think what I'm saying is there's a difference between signaling and representations.
Well, I can redefine I see what you're saying. Yeah, there's a difference between like a hardcore, like a hard representation where I can pinpoint, like here in the brain is the representation, and me saying that, just kind of the activation pattern in the brain is the representation, but it leads to the same end thing. Somehow we need to tell the brain what's going on, right? In this high level. Yeah, it means, I think he has a slide on this later where he explains it more closely. I mean, just like that, it just basically means very little.
Well, here's why I like the generator model so much and exploring the latent space for these factors that then change. So in this latent space Z, even in like a style GAN, that's trained on faces only, you can find a car in that latent space. Like there's papers that find all the images in that latent. Okay, we can use supervised learning to get the glasses and the hat and the beard clusters. And now we have the car. Now we give it car. Like, does this cluster still make sense? So we have this cluster that's doing the Z's, and we've attributed that to glasses. Now that the Z's now that we found the Z's that generate cars, like this overlap, I think, is of the idea.
I can see something where you'd say, here is a cluster, even though I'm only trained on faces, I can kind of sort of produce a car, right? I can do this with disease over here. And then if you really learn about cars, your entire model now changes as well, so that maybe these latent representations become more probable and so on. I mean, I see what you're saying, and it is very plausible that by basically having this generator and going from the latent space to the real world, we learn about concepts. I mean, I can get on board with that.
Maybe a better example would be if we're trained on only like male faces, and then we have a woman face with glasses, and the glasses Z vector is still the same. So we found the area of the Z space that's producing women, and then the glasses part of the Z vector has a high overlap, maybe. Instead of cars.
I agree that at least not in terms of consciousness or anything, but what he's saying with the robustness to distributional changes and the rules stay the same and so on, that might be a good example of what he's talking about. Basically saying glasses on a one type of face are still glasses on the other type of face, and you should use the same components of your generator to produce these glasses. Well, it's an interesting point, right? I'm pretty sure GANs that exist today can do this glasses thing. Like we have GANs now that can modulate independent factors, and you can transfer these independent factors to other things that you've never seen before. This is all possible. It is not system 2 by any definition we've had so far. So it's all kind of mixed here, right? It's all system 1, because ultimately we just build one neural network, one forward pass, boom.
It just doesn't make sense to me, though, because as we were talking about last week, we're talking about models that have almost no generalization, that are learning very fixed manifolds for particular types of semantic informations. We build a fixed factor graph. How is that making progress or generalizing at all? What's clever about that? It seems like it's a fixed prior that has been created by humans so far. So that's talking about system 2 generalization. That's the recombinations in system 2 world.
So now let's talk about what is maybe the most interesting property of system 2 cognition. And that is the ability to do what is called systematic generalization. This is something that was studied a lot in linguistics, where humans can dynamically recombine existing concepts to form a new concepts. Be verbal, but it could be visual, like in this example from Lake et al., where different types of vehicles are combined to form a new one. What's interesting is that recombination allows us to explain observations that not only we have never seen, but they have zero probability under our training distribution. Like if I tell you a science fiction scenario, or you're driving in an unknown city where the drive is very different. Up to now, what we have observed experimentally in a number of papers is that when there are such changes in distribution, current deep learning systems don't perform very well, and they tend to overfit to the training distribution, not just the training data. And so we have issues of transfer that doesn't work as well as what humans seem to be able to do.
I just disagree here. Even when new combinations have zero probability under the training distribution, like driving in an unknown city, like that, it just, I mean, you have to define your training distribution so surgically to make that happen, to make the probability zero. You basically have to say you're only allowed to train in this one. It's a forceful reduction of your training distribution to that driving in an unknown city has a zero probability. I just take issue with the zero probability thing and the fact that should be something special. Because
let's make the assertion that the training distribution for any computer vision data set, it's combinatorially large. You would never ever have anything that even approaches a representative sample of the distribution.
But it is hard to come up with an image that has a zero probability under my training distribution. Almost any image will have a close to zero probability, but some zero, like, and I don't see what's so special about having things having a zero probability under the training distribution. What I can see here is that he basically talks about, okay, if there's distribution shift, then humans tend to adapt more quickly and better than current machine learning systems, which is true.
But I suppose what he's saying here is that you can build models to learn some kind of first-class semantic objects in your images. So motorcycles, people, scooters, unicycles. So rather than capturing the combination in system one, it's almost like you break it up into intermediate steps. So you capture the primary colors or the first-class citizens in system one, and then in system two, you do the recombinations.
So we have supervised, we have our bike, and we have the different Z factors that produce bikes, right? Maybe the system two is then distilling the different factors into this guy on this unicycle, motorcycle, whatever this picture is. But it's like, that's the system two part, I guess. So what I think he's saying is that system one, we produce these, we have disentangled representations of this. I think there's a Segway, and then a motorcycle, and then a unicycle. So it's and then combining the disentangled representations is a system two thing.
It could be, but again, I ask, what is the probability under your training distribution, not data set, under your training distribution of this monstrosity? Right?
Yeah,
it's not zero.
Right. I think it's back to just the energy-based models versus probabilistic models. It's maybe not the best thing to be trying to push things to zero probability.
Yeah, I mean, yeah, I get it. What he's saying is that the machines aren't yet very good at doing this generalizing, what you're saying, this recombination of things that they know in unknown ways.
I mean, that's the bit that's exciting. For Chollet talks about the four different types of generalization. There's absence of generalization, which was the case in traditional expert systems, and then there's local generalization, which is what machine learning does now. So the ability for a system to handle new points from a known distribution for a single task or well-scoped set of known tasks, given a sufficiently dense sampling. So that's what we have now, and what we want to move to is this broad generalization. So that would be like the Wozniak coffee cup challenge, where you have, a robot can go into any single room and make a cup of coffee. And I think this is a step in that direction, because he's saying that you can find combinations of semantic objects that in all likelihood, let's just say it's zero probability, in all likelihood would not have shown up in your training distribution.
Yeah, but these distinctions between local and less local, we're very close to building a robot that can go into any room and bring you a cup of coffee. Like something Go Explore combined with some model predictive control. It'll soon be able to do that. And the people will say, well, that's just local generalization, right? Or even expert systems. I can build an expert system, and then I can ask it a question that not only has it not heard before, that no human has ever heard before, and it can answer it correctly. And so this kind of levels of generalization, not buying it. It's the same thing. It's just okay, the scale is different, but
well, I think Chollet would say that the Wozniak coffee cup challenge is broad generalization, the ability to handle situations that could not have been foreseen by the creators of the system. So if you think that we're close to doing that, then that is broad generalization.
But again, if you build an expert system, I can ask it a question that you have not foreseen, because no human has foreseen it. Because no human has ever thought of that question, and it can answer it correctly.
But the difference is, in the expert system, you could enumerate analytically the space of possible questions and answers.
Well, yes, but in the space of robot coffee cup gatherings, if you discretize the world to a fine-grained grid, you could analytically enumerate all the possible things that could happen there.
But that's not the way that these control systems work, though. They work by creating some kind of representation which will have some kind of generalization to different situations.
So the expert systems, they map your questions to a regular expression. It's not like they have all the questions and answers as a lookup table. They map it to a representation, which is a regular expression, and then they do their logic rules with that, and then you get the answer to a question you've never ever seen before or thought of.
I mean, Chollet is really skeptical about deep learning. He says that they're a bit like hash tables. Deep learning is basically a hash table, basically an expert system, because in an expert system, you have regular expressions, for example, which make a useful representation of a string. So if you were being really cynical, you could say there's no difference at all between the original expert systems and deep learning.
Not qualitatively, no. Okay, the qualitative difference is one is learned from data, or one of the inputs to it is training data. But that's really all. You still need programmers and whatnot. You still need priors. You still need the computer. I don't see really a qualitative difference, and I'm not going to see a qualitative difference with Wozniak's robot that gets me a coffee cup.
Well, the regular expression mapping is nowhere close to as expressive as these transformations in deep neural networks.
Sure, the quantitative difference is very apparent, but the qualitative difference, I don't see it.
I just generally in generalization, I don't think the coffee cup example is very good for generalization. If you just show it enough rooms, it'll be able to get it.
I'm not so sure about that. It's not just about the rooms, though. It's a little bit like playing chess. You would think is really difficult. If you ask someone in the 70s, what's harder, playing chess or picking up the telephone and talking to your grandmother? Actually, the telephone one is harder, because it's not just about picking up the phone. It's about all the natural language processing and the speech recognition and God knows what else. There are so many cognitive tasks that would require specific skill programs to implement.
You can transform the Wozniak. Was it Wozniak? Sorry, I've never heard this. Okay, yeah. So you can transfer this example because he kind of leaves himself a sneaky door open in that he says, it should get me a cup of coffee, whatever happens in that room. So, if that room, there is like Gary Kasparov there, it's like, robot, you play me in chess right now, or you won't get this cup of coffee. Then it just reduces back to general intelligence. Then the robot and the coffee cup is irrelevant. It's just like, if I can put an IQ, basically, I can construct a room with an IQ test, and you only get the coffee if you solve the IQ test. Then, so the example leaves a sneaky back door where it just reduces to AGI or human level intelligence. Well, the qualitative difference from deep learning to expert systems is that I can do a PhD in deep learning. I'm very thankful for that. So,
how does that relate to the symbolic AI program, the classical AI, good old-fashioned AI? To get the best of both worlds. We want to avoid the pitfalls of classical AI rule-based symbolic manipulation, to keep some of the things we have achieved with deep learning up to now. So efficient large-scale learning, semantic grounding in system one representation, all of that implicit knowledge I talked about. We want to keep distributed representations. For example, symbols would be represented by vectors, so that we get better generalization. And we want search, which is something that mostly happens on system 2 side, to take advantage of the power of system 1 to guide the search. and thus to be efficient. And finally, of course, one of the advantages of modern machine learning that we want to keep is the ability to handle uncertainty properly. But we want some of the advantages that are associated with System 2. I mentioned systematic generalization. It's connected to a knowledge representation idea that knowledge can be factorized and composed into small exchangeable pieces in that manipulate variables, instances, references, and indirection. One of the important messages of this talk is that in the last few years in deep learning, we have made progress with tools such as soft attention, which might be a key to a transition from the old deep learning, where we process vectors, fixed size vectors, to this extended deep learning in which we actually manipulate sets.
I think at least to the neat uncertainty handling point of this, I agree. I don't think humans do that well. I don't think humans handle uncertainty well. So if we're talking about human level intelligence, that's not something we need, but it would be nice to have. And here he talks a lot about search, that he wants most of the search to happen in System 2. And that brings me back to the beginning almost, in that he seems to view System 2 as something where you have to perform some kind of manual mental labor, spend effort to do a search in this kind of space of these latent variables. So it's almost like you have to go step by step by step and do this manual search down a logic tree until you find something like, this is how I get to my goal, right? And each of the steps in the search tree is something that System 1 could handle, but it can't jump to the solution. I think this somewhat becomes clear here that System 2 can be conceptualized as searching when you don't know yet where you want to go. But you want this to be guided by System 1. And here the analogy that could be made is maybe something like AlphaGo, where you could train an RL algorithm that would just reinforce policy gradient. Bang, here's a board situation. This is what you're going to do. But this will not work as well as if an AI algorithm that can do the search. So what if I do this? What if I do that? And after that, what if I do that? And so on. You go down this tree. But we can't go down the whole tree because it's too large. So we use deep learning, we use the neural networks to guide this search, to say which are the mental steps that we need, the elements of our plan that we need to explore or that are promising to explore next. And that is informed by your intuitive System 1 thinking. So I think it just makes it a bit more clear what he sees as these two systems and where he sees them connected. And I mostly agree, actually, with this kind of thinking.
Yeah, I think you nailed it with the Monte Carlo tree search AlphaGo comparison too, because at each, the Monte Carlo tree search, it looks for the best action, and then as it puts out all these potential next nodes to go to, and then it uses its intuition or its policy and value networks to choose which ones of those to go to next. So I think that's just the perfect analogy for describing that.
It says need efficient large-scale learning. Isn't that an oxymoron? Large-scale learning means sample inefficient brute force learning with millions and millions of iterations. Isn't that the antithesis of efficiency? Isn't that what we want to get away from?
Maybe what he means is that you need a way to efficiently learn from large data, like a bit like Yann LeCun. So I think maybe he's referring to. So what the title is, we want to avoid pitfalls of classical AI, rule-based systems, and these would be very expensive to compute, and therefore, if I want to learn a classical AI system from data, I have to do this expensive computation because that's basically the forward pass of the model, and that would not work well with large data sets. So he basically says we want something that is able to incorporate large amounts of data. And this connects well to what Yann Lecan said when basically the future is self-supervised, in that system one here could be a system that consumes this large amount of data and kind of tunes this intuition to the large amounts. I think it's just saying that we need a system that is able to do these kinds of things, these search and computation, but can handle lots of data.
But deep learning is not efficient. Even with the self-supervised stuff, it doesn't do anything to address the sample efficiency of deep learning. He also says that we need distributed representations for generalization. Again, as we were just saying, deep learning models do not generalize. That's the whole problem. They have minimal generalization given a dense sampling of the input space. So it seems to me that he's talking about the pitfalls of the classical symbol-based manipulation. If anything, these are the advantages of the classical space manipulation. What we want with System 2 is the ability to learn quickly, think slowly, but learn quickly. And we want to have representations that generalize well. We don't have that with deep learning.
That is true. I agree with Bengio. We probably need distributed representations for generalization, because the alternative would be to have basically pointwise representation, right? Unique representation and not distributed ones. And for generalization, if all of your space is separate and discrete, you have almost no chance of generalizing. You only get that with a distributed representation. And then, the large scale learning, you're right. I think if you were to question him on that, he might also, I'd be very surprised if his opinion was that we need lots of data to learn the System 2 tasks. Maybe what he means is that the System 1 task that informs the System 2 task can handle lots of data. I'm not sure.
I mean, another thing is it says needs uncertainty handling. Now, again, this is maybe this is a trick question, but do you think probabilistic graphical models are symbolic rule-based programming? I would argue they are, in which case you can do uncertainty handling.
Humans don't have good uncertainty handling. Deep learning doesn't have good uncertainty handling. And the fact that in a graphical model, I can kind of compute the uncertainty accurately is counteracted by the fact that I have to create the graphical model from my mind. Like, I put it down. I impose the structure of the graphical model. So the accuracy of that uncertainty is going to depend on how much that structure fits with reality. And I would say you probably have no better chance that your uncertainty there is your actual uncertainty in the real world than with a deep learning model, just because you can put a number on it.
Indeed. I do agree with Bengio, though, that this notion of once you have a factor graph with these semantic variables in, you can have this recombination and you can have this systematic generalization. That seems logical to me. And I agree that factorizing knowledge into small exchangeable pieces, of course, seems completely reasonable to me. But how do you do that? He hasn't really given us any indication on how we would create these factor graphs programmatically.
I don't think he ever completely gives you the algorithm for it.
Maybe I've misunderstood his presentation. He talks about, given a fixed factor graph, which he's created himself, you can learn about the causality between them based on the convergence behavior. That's completely different to how do I get this factor graph in the first place.
Oh, yeah. That refers back to what we talked about before, that if you want a sparse thing, we have no idea of how to learn this.
Well, I don't know if I've sold you guys on this yet, but the idea of looking in the latent space with something either supervised or semi-supervised learning, I think that really would produce some kind of causal graph in that Z space. And I think you could discretize the Z space to some level. Not really super fine grained, but.
Yeah, but is it sparse? That's the question, right? Because we only know how to learn fully connected things. And especially, like, we can like quantize and trim and prune after the fact, but we can't learn sparse things like from the get-go. And the question is clearly, if what Bengio says is true, we must be able to directly learn a sparse factor graph because it's just too high dimensional. Like we can't have every variable connected to every other at the beginning. And I know babies have more connections and stuff, but still, that's a whole other level.
I don't follow you on that, because why could we not learn how to prune? I mean,
we can learn how to prune, but what I'm saying is that in order to prune, you first have to have a fully connected graph. And if what Bengio says is true, that we basically operate in the space of these discrete concepts, of which there must be like many, right? And that works if there are many, as long as they're sparsely connected. But we cannot, it's not physically possible to learn a fully connected graph between them and then prune, because we don't have space for a fully connected graph.
Yeah, so this is like the catch-22 situation with the lottery ticket hypothesis, is that you need to start with the big one and then go down. But unfortunately, it kind of defeats the purpose a little bit.
We don't know how to learn sparse things, because at some point you have to connect the thing to the thing, because you make a new experience and you connect these two things. But what you don't want is to what we do right now in neural networks, especially with things like attention. We connect everything to everything with a really low weight, and then the gradient tells you put it up a bit.
Yeah, and it wouldn't be learnable if we did it any other way.
Yes, because hard zeros aren't amendable to gradient descent. So yeah, as I'm saying, we have no clue of how to learn sparse things. I like your idea of this, and I'm not saying I agree with Bengio that this is the situation, that this sparse factor graph, because I see the problem. We do have continuous representations for sure, because we're able to interpolate. What you're saying, we have this latent space and so on. We could discretize it, but sparse.
So we're talking about learning to prune, so starting big and getting smaller. Can't we do the reverse? Can't we start not infinitesimally small, but small with a dense sampling and learn to grow?
So you mean you would dynamically add these concepts, the variables?
Yeah, start with something which is densely connected enough to have a gradient and be learnable, and then build it out progressively.
So when you would learn something in Bengio's version, you would only have very few of those nodes. So initially you would only know about dogs and cats and not about the rest of the world, and you add things. I mean, that's possible, but still, if you add a new thing, what do you connect it to? And if at some point you need to revise these connections, how are you going to do that without iterating through each pair of connections?
Doesn't this get to the elephant in the room, which is that it's not learnable? If you want to have this kind of semantic worldview model, it's just not learnable.
Well, humans are learning it, so somehow it must be possible. So far, maybe I'm not technically seeing how one could learn something like what Bengio's proposing. Like it has the three attributes: discrete, sparse, and independent. That means the same as sparse. But yeah, that is they just don't go with each other.
I'm kind of reaching for something here, but in our poet algorithm, as the environments start to get more complex, and it's not through gradient descent, would you say, like, okay, so these complex environments, they start simple. I think Tim is really onto something with this idea of like maybe like the neuroevolution of augmenting topologies, where they start off with like one node and then they evolve the structure. So the complex environment that arises at the end of that, maybe this is what's happened. Maybe there's a coevolution between the dense representations and the sparse thing, and they kind of interact in a similar way as our bipedal controllers and then the environments. This is the thing, the dense thing is what's using gradient descent. This is using just evolution search, these no gradient descent techniques.
Yes, but that would mean you could do the dense thing only ever in a very small subspace of the sparse thing, right? I mean, this is possible. This could be a way that you basically are revising this part of the sparse graph and then this part and then this part. Yeah, I can see something like this.
Which one of you is going to pivot and change your PhD to this new research idea?
Not going to happen.
Which reminds me, we should do an episode in the future about both of your respective research topics. I think that'd be interesting.
Yeah, I think the coevolution of sparse and dense, I actually think there could be something really interesting to that. I actually have had a few things we've been talking about. I've been trying to think about how I could write a paper about that.
Well, I've been wanting to do sort of streamed research for a while. Like, okay, I do a PhD and I need to write these papers, and I'm kind of relying on no one scooping me, so I can't really share my process. But once I'm done with this, when I'm going to write a paper, I'm going to stream the process, or at least make a video continuously about the facts. Like, here's my idea, blah, 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 blah. If someone scoops me, who cares? Right? I mean, but I think it will just be so much more fruitful to share this process with the community. And maybe a new way of research can be, or probably not though, because people still have careers and stuff where they need their name on things. Yeah.
But it could be really transformative, because so many people might transform your research direction in real time.
Our citation system is ridiculous, isn't it? That you need to be the author of the paper.
I've been wanting to revise the citation and publishing system for a while.
Okay.
One of the important messages of this talk is that in the last few years in deep learning, we have made progress with tools such as soft attention, which might be a key to a transition from the old deep learning, where we process vectors, fixed size vectors, to this extended deep learning in which we actually manipulate sets. We can focus on a few elements at a time. Soft attention had a huge impact on natural language processing, starting with machine translation. Allows us to learn where to attend. And interesting neuroscience results suggest that this attention is like an internal muscle, an internal action, and that it's processed in the brain in a similar way. It allows neural nets to operate on sets. And it's at the heart of several theories from neuroscience about consciousness, in particular, the global workspace theory.
With respect to attention being present in the brain, I think that is certainly correct and really important, but also I think that's not consciousness. It might be necessary for consciousness, but just because you have attention, you don't have consciousness. To me, consciousness might arise from the attention mechanism being able to attending itself, which we don't have. And the question is that the consciousness, or is that just how a brain works without consciousness?
Well, does attention need to attend on itself, or does it just need to be one hierarchy? Like, this attention attends on this attention, and this higher one is the consciousness. Like, do you think it needs to be on itself, or isn't this just one step hierarchy enough?
For it to be consciousness, I would argue that the attention needs to be attending itself. Because I can build right now a system that has 50 layers of attention and no consciousness.
But if it's a meta-learning system where the outer loop is attending on the structure of the inner loop, and then they're entangled in some way, isn't that enough?
Still not gonna get anything conscious out of that. I don't think, at least.
I think, yeah. Well, I also think it has to arise out of a very complex situation too. The higher dimensional, the input, the more diversity, I think that kind of complexity also plays a role in that kind of this attention to attention becoming very expressive.
Maybe, but if you look at the input, it's not so high dimensional, honestly. Like, you have vision, that's 3 channels. You have audio, that's 1 channel. You have tactile, that's a couple of channels. You have olfactory, that's a few channels. It's not so high dimensional.
Well, maybe it is. Maybe it's possible, but it's definitely not possible now, right? Yeah. Like, to build a not even classify, a reinforcement learning system that operates on 4K images while simultaneously super high resolution speech. Yeah. But that kind of system, maybe that is what's going to happen.
Maybe, but you'd have to count on there being some sort of phase transition once you get to a high enough dimensionality and modality. Maybe it's entirely possible. Ultimately, we're nothing more.
Because it's also a bit back to our coffee cup thing. Like, if you have enough dimensionality, I think it becomes like this really crazy compression engine then. And it's also like at the scale of the data, it's seen so many coffee cup rooms that it can figure it out.
But what causes it to all of a sudden go, I've been seeing many coffee cup rooms lately? Like, I don't see that just the fact of scaling up that eventually that would arise, except if you have attention attending itself. And that I see as a built-in feature and not as something arising from just, having higher dimension. I could be completely wrong here, by the way.
But don't you think we've already seen this phase shift? Like just the fact that if you give it 1,000 cats versus dogs, and then compared to 1,000,000, like haven't we already seen that exists?
No, my ResNet is still not telling me about itself.
Okay, I understand. But the phase shift idea with respect to higher dimensional inputs and then more data, do you believe in that existing?
It could be. Like, I have no clue, right? I'm as clueless as anyone about this, but I just don't see that simply the act of scaling up will all of a sudden qualitatively shift the system from interpolating the training data to suddenly becoming introspective about itself and being able to express that.
Right. I think there's two things at play, but I think that with respect to scaling up, the interpolation just becomes so powerful. It becomes really hard to tell the difference between that interpolation and generalization. But then the next idea of explain itself, I think that's totally different.
And it's at the heart of several theories from neuroscience about consciousness, in particular the global workspace theory, forward by Bars, but also by Dehaene and their collaborators. Involves a bottleneck of conscious processing. So information is selected with attention from many possible modalities and the input, and the selected items are then broadcast to the rest of the brain, as well as stored in short-term memory to condition saying perception and action in the short term. And this enables sequential processing, conscious reasoning, planning, and imagination. One interesting thing to note here is that if we think of the brain, in particular cortex, as a big simulation engine that enroll some kind of imagined future, it does so in a very special way. It's not like a movie. It focuses on a few aspects of a movie at a time, at each step of this simulation. So
he's not saying it explicitly here, but I think that is how System 2 interacts with System 1. So it says nothing particular about System 2, in fact, but it says something about... So I think the model is that he puts up here is sort of like the brain is now operating in this logic space of System 2, right? And it has an object it thinks about, like a dog. So what it will do is will broadcast to the rest of the brain the distributed representation of that dog, and all the parts of the brain will basically answer with what they know about this signal. So you blast out like dog, 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 and then all of your parts, your memory, your audio memory, your tactile memory, and so on, they will all send back what they know, and then this System 2 is somehow tasked with integrating that information and then kind of going to the next step of its logic processing. It tells us nothing much about how that logic processing happens, but I do like the idea that this is how System 2 interfaces with System 1. Because System 1 is the thing that would just send back the information, right, given this signal.
The thought occurs, why have we not tried to recreate something like this using a neural network architecture?
Well, maybe it's hard. I don't know. The question is, what does System 2 do? I
think you articulated beautifully what Bengio was talking about.
Yeah.
And it made me think that our brains there's no nexus of computation. There are distinct systems and There are broadcast messages that get sent between the systems, and possibly the prefrontal cortex is the mastermind that does some kind of, maybe it has precedence over the other systems. But why have we not created a neural network architecture somewhat akin to that? Why
there are
the architectures we create are just very linear, just left to right?
There are things like memory networks where you sort of store information in this distributed way and then retrieve it again. But what you can say, it is drastically different, for example, from let's say a transformer. A transformer, you simply forward propagate your input through the layers. And the knowledge about the world, or the knowledge about language, is stored in the connections between the layers, like in the weights. Whereas this model would say something like, here you are reasoning, and then you're retrieving information basically from the rest of the brain by attending to one particular part of the computation that you would do. So I think you have a point. Maybe we should go into building more of those systems.
What's the difference between top-down attention and bottom-up attention? I think of something as like BERT as being bottom-up attention in the sense that it gets the input and then it's like attention, attention. Yeah, maybe if you had like the features, it's like CNN, convolutional layer, attention. That sounds like top down to me.
Well, I'm not sure, but maybe top down is something where you have like a sec to sec in RNNs. So what you would do is encode your entire input sequence. And then once you decode your output sequence, that's when you generate the attention queries to go back to the input sequence, right? So when you, at that point, top down, basically you say, oh, I need to produce this thing here. What do I want to gather? Whereas, in BERT, as you say, you always make the attention from the input. I mean, ultimately in the RNN, it comes from the input as well.
So the connection between consciousness and language is very strong. In fact, this is almost the way in which we know that some event is conscious versus unconscious, and that is that people can report it verbally. It's also important to understand that we need to tie those high-level representations with lower-level action. There's a lot of knowledge about the world that cannot be represented, those strong assumptions I'm talking about. And so in order to understand language, we need to have both kinds of knowledge involved. This gives rise to research in things like grounded language learning. Let me talk about this very basic.
Yeah, I think I'm kind of worried that this idea of grounding language and vision is going to be where academia gets completely left behind. If now they're built, like this is going to be to me like this large scale kind of thing, that this is where we'll see the 100 billion parameter model is something that's doing language and vision simultaneously.
Yeah, maybe, but maybe you can just take these pre-trained models on the data modalities and then learn a system too on top of those. Nowhere here does it really say you need to learn them jointly.
Let me talk about this very basic prior in my list, which I called in 2017 the consciousness prior. The idea is that your joint distribution of these high-level variables is sparse. So if you think of the joint as represented by a factor graph, think of each factor involving a few variables like a sentence. There's an amazing property of high-level knowledge like this, which is that in a single sentence, I can make a probabilistic prediction that is very strong, that has a high probability of being true, in spite of the fact that it involves very few variables. So if I say, if I drop the ball, it would fall on the ground. I'll make a very strong prediction, but it involves only a handful of concepts. Now, this is different from the common assumptions of marginal independence, where we assume that high-level variables are independent. Then we have these dependencies. For example, ball and hand are not independent. And this also connects to the notion of attention I just talked about, because when you want to do inference over such a sparse graph, a reasonable way of doing it is to focus on one or a few factors at a time, just traveling in that graph in order to iteratively change some inferences.
It makes a lot of sense what he's saying. It's just a question of, first of all, how do you learn such a thing? And second of all, how does that connect to the fact that you have distributed representations? Like this is what I've been criticizing, sort of, that the distributed representation that appear to be sort of continuous. How does that connect with this very discrete, sparsely connected thing?
I'm really confused because he's talking about such an abstract concept. I have no idea how this factor graph comes into existence. I mean, yeah, I get it. You know, there are all of these semantic things inside your image, and you can disentangle the factors, and you can create this sparse factor graph to model the joint distribution between them, and then you can do all sorts of clever stuff. But it's just, how do you get there?
I mean, don't you think that's like overly simplified too? The idea that it's just like an atomic ball is a node on the graph, and then like hand is this atomic other node on the graph?
No, I think that's what he means. That is in fact what his idea is, that you have these objects, and these objects are sparsely connected with these factors. And so the objects here are ball, ground, and hand or something. And the factor that connects them is, if you drop it, then it falls on the ground.
I mean, would it be possible to learn these factor graphs in a supervised way? So imagine if, given a whole bunch of problems, I tell you what the factor graph is, and then a new unseen problem, could I predict the factor graph?
Yeah, I mean, that's his point, right? That somehow, if this is correct, somehow humans are able to learn this factor graph. And then when I, change one part of the factor graph, first of all the others remain. And second of all, the relationships still remain. So if I get a new idea of what a car is, like, okay, there's now this Tesla thing, and it's something completely different, but it's still a car. I can just plug it into the node for car, and all my rules will still apply, right? And if I learn something about the car relationship of cars, like, oh, we now drive left or right, whichever contour, right? If that changes, then that applies to all the cars, including the Teslas.
Let's talk about the assumptions regarding how things may change in distribution. This is a very, very important hypothesis that I think provides some of the great power of conscious processing. So the picture you should have in your mind is there's raw data which has a very complex joint distribution, but we're going to represent it with two levels. There's an encoder that maps that raw data to an abstract space, these high-level semantic variables. And what happens when there's a change in distribution, according to this hypothesis, is that abstract space, the change is localized. Maybe just one variable, one conditional, or one factor needs to be modified. Consequence, it becomes much easier to learn to adapt to the modified distribution. So you can have fast transfer to represent information in the right way.
So that's basically him saying, how could you attempt to learn such a thing? And that is the regularizer that you'd apply. So the regularizer is, if something changes in my input through an action that I do or something, then I can only change one or two things in my factor graph. That's essentially, it's a regularizer for learning such a thing. And then also for inference, it's a yeah.
Is the implication that the encoder creates the semantic variables or the factor graph as well?
Both, yeah.
Okay, and that's via some hitherto unknown mechanism.
Probably the decoder creates the encoder creates a representation, and then you have some way of mapping that representation to the nodes in the factor graph. Sorry, yeah. I mean, cannot speak for Ben.
Because the encoder ends up being totally deterministic, and it's the latent variables that are really the thing, I think, right? And
yeah.
So it's like latent variables and then the sparse factors. And how do you disentangle that, I guess?
Yes.
Because he also makes the comment on the slide that the change may be drastic in pixel space, but tiny in the semantic space of causal variable as well. Of course, the whole point of deep learning models is to give you semantic information irrespective of, completely normal changes in the environment or what.
But this comes back to this discreteness and sparsity of the factor graph. If he would model consciousness as being in distributed continuous space, then he could not make a thing like well, he could. That's basically what the disentanglement crowd is saying. The disentanglement crowd is saying there is this distributed continuous space that you operate in. And if you make a big change to your input, then only one of the dimensions changes. Bengio here goes a step further, and he basically says there are these discrete variables that are sparsely connected. And if I change a big thing, only one of those will change. So it's the same thing, but in a discrete, sparsely connected way, instead of in a continuous distributed way.
Well, so once you've disentangled the factors in the Z representation and they're discretized well enough, it becomes like a super node. Okay, so we have a 5-dimensional vector, and now it's sparse such that we have 1 is like taking on 1 of 10 values. So that's like a node, the littler node, and then say the 4th spot in this 5-dimensional vector is taking on 1 of 10 values. These are the 2 nodes that make up this super node that's connected to the other node. So then the idea would be, can we like take apart the nodes within the super nodes? Is kind of how I'm thinking about it.
Yeah, I kind of get, but he makes it explicit that what he's talking about is not the same as disentanglement, because his factors can be entangled, but just sparsely. And sparsely meaning also sort of independently. So it's not like there is a rule to how the sparsity arises, because then that would limit your capacity.
And the interaction effect.
Yeah.
The Z thing might have finally been defeated. I don't think I'm ready to give up.
I'm a fan of the Z thing. I'm just saying that's probably what Bengio's thinking of.
So we actually tried this idea in simple settings, first with variables A and B, where you learn through changes in distribution that involve intervention on one of the variables. And we find that the speed of learning is a good clue for you have the right hypothesis, the right set of high-level variables, and whether A should be the cause of B or B should be the cause of A. Recently, I ended that work theory side to prove that this adaptation wants to converge to the right hypotheses. So extended it in the direction of large.
Now, this is where it gets really interesting. One of the key problems with deep learning, as cited by the causality crowd, is that there is no way to tell if A causes B. Now, let's make this a bit more concrete. So, it can be a variable. So you were saying A could be a hand, B could be a glass of water. And this corresponds to X's and Y's, and we can reformulate it in both directions. And so the first thing is, how do we disentangle A and B? And the second thing is, once we've done that, can we learn a causal relationship? And he seems to be suggesting that by looking, if you look at the convergence behavior on the training, A to B converges much quicker. So we can infer from that there's a causal relationship. I mean, that seems pretty interesting.
I mean, what we know is that ultimately we should get to the same result, because whether or not A causes B or B causes A, their correlation is going to be the same. And deep learning will only ever, focus on the correlative aspect of data. But I think that's pretty smart here. I'm pretty sure the causality crowd is kind of on that, is asking how easy is it to learn A from B or B from A? And here the proxy we take is how many SGD steps or something like this does it take with one model versus with the other model. I think that's quite smart. Again, nothing to do with consciousness, but smart.
Are there any engineering pitfalls here? Because just measuring the convergence behavior is tricky. So many factors influence it, and it would need to be a fair experiment.
Oh yes, especially automatically determining this. I mean, yeah,
it's surprisingly difficult even to know when to stop training, or being able to characterize one convergence from another is surprisingly difficult.
Yeah, plus you will only have this graph, right? You can only test these two directions in this graph. This says nothing about whether or not that's the actual correct arrangement of the graph, whether there is a variable C that is a confounder that causes both A and B, right? Even then, you're going to learn one direction faster than the other. It could still be that there's a confounder, that there's a mediator, that there's like a billion other things. But in terms of learning the causal direction, I think it's pretty smart. Yeah.
Would you quantify this in a contrastive way or in an absolute way? So would you say that this looks like a fast convergence in an absolute sense, or would you have more of a comparative or relative thing? Because as you say, the graph could be significantly more complicated, and the more factors you have, it would probably flatten the convergence behavior. So you might need to have more of a contrastive approach.
If you just determine that this is the graph and you just need to figure out which one is the direction, then you can do the comparative, the relative, right? Just which one's faster, which one's above the other after this many steps, or generally. But if you're not sure that this is the graph, you have no chance.
A quick side note with causality. Is it possible to have a transitive causality? So I do something, A causes B causes C. Could you say that A causes C, or is it only one hop?
You mean terminology wise?
Well, just philosophically speaking, it's possible to have multiple factors. B could be caused by A, C, and E.
Yes. And so in terms of do calculus, in terms of maybe Judeo-Pearl language, you might say that A causes C in that, because if you perform an intervention on A, that will cause a distribution shift in C. So that would be a causal relationship there, but that's an opinion and the terminology.
The direction of larger graphs, not just two variables, with the fact that the number of such graphs is exponentially large, parametrizing the graph simply through its edges, and shown that you can do fast causal discovery using this method. A bit of work.
Right, just to double check, what exactly does he mean by factorize a joint distribution? Does he mean make it sparse?
Yeah, like make the causal graph and make it sparse is a requirement such that you can actually handle it engineering-wise. You could factorize it fully connected, but I think he means in a sparse way, yeah.
So let's say we have three variables, X, Y, Z, and the joint distribution they each take on, say, three values. So you're factorizing it to say X is taking its third value, how that connects with Y's second value and Z's second value?
Well, factorizing in here is equivalent to drawing the causal graph. And you generally assume that these causal graphs are sparse, because like this whole assumption of I change one thing that's going to influence the two next things, and then there's no direct. So for example, if there's rain, then that will cause my roof to be wet, and then that will cause water to come down the drain, right? So, but then we don't need an arrow from rain to water down the drain anymore, because we have an arrow from rain to roof and from roof to drain. And there is no additional causal effect from the rain, because we know the rain is not going to run around and kind of go into the drain from the bottom without first hitting the roof. So the kind of assumption that this is sparse comes from the causal structure of the world generally being sparse. But in terms of factorizing, just means drawing the causal graph, determining the causal graph from data.
So sparse as in terms of the cardinality of the values that each variable can take on, or sparse in terms of connecting several variables in the joint distribution?
Yeah, the connections are assumed to be sparse, or generally sparse in the world.
Okay, cool.
A bit of work I want to mention. It's on some of these hypotheses, in particular, the composition of knowledge into pieces that can be recombined dynamically is they're called recurrent independent mechanisms, where we define a new recurrent neural net architecture in which, instead of having a homogeneous network, we break the recurrent net into smaller modules, where inside each module it's fully connected. But between modules, there's a attention mechanism, which you can think as where consciousness is focusing, that selects which module is talking to which module, and module is sending value pairs, so essentially variables, have a name type as well as a value. And find is that this kind of architecture leads to better out-of-distribution generalization.
It leads to better out-of-distribution generalization, but less accuracy. Probably. I don't know, but it's a cool architecture, but I guess it's not going to work as well for most problems. Yeah, since this is an RNN, right? Since this is an RNN, what it does is it kind of does some computation, then it sparsifies that computation, and here it's done via attention, but I'm not sure if the attention really, this just bunches together a bunch of things. So it's in essence a computation, then it compresses, and then from that compressed representation, it takes the next input and does the computation again. So this can be akin to the brain, doing some reasoning and then sending out, getting information, computing that, and doing some reasoning more. But it's very abstractly connected to this. And then the fact that attention is used to send these things around, fine. But I still fail to see what that really has to do with consciousness.
Let me summarize and conclude. This brief talk, I've tried to sketch a direction of research for deep learning, words capturing not just system 1 knowledge, but also system 2 knowledge. And what I find is that this involves many interesting research aspects, things like out-of-distribution generalization and systematic generalization, representation of knowledge in a modular way that allows fly compositional dynamic computation. Connects to meta-learning because we can learn the stable part of the knowledge as well as how to, on the fly, combine those pieces together. This relates to cognition and neuroscience, especially of attention, reasoning, and consciousness, and it relates to agency and non-stationarity. The priors can be listed, and I'm sure we'll find more, but maybe the central prior is this idea, two central priors that I've tried to highlight is one, that knowledge can be decomposed into recombinable pieces corresponding to dependencies involving very few variables at a time, and that the way that knowledge changes over time is local, involving interventions that involve only one or a few variables at a time. So this is interesting because it allows an agent to learn faster how to adapt to a change in distribution, or maybe even just do inference in order to discover the reasons why the change happened. Connects to natural language. It connects to the problem of discovering causal dependencies. Connects to the question of how meaning in natural language be associated with both the system 1 knowledge that relates perception to those high-level variables, and how these high-level variables interact with each other in this very structured way.
I think you said there is that knowledge can be factorized. It can be decomposed into these relations, which can be recombined to generalize in lots of out-of-domain situations. That seems completely reasonable to me. But I would still argue that the apparatus to create those semantic relationships in the first place is still ineffective in the same way as it is now with deep learning.
Do you think of features as a good semantic variable?
Features often are semantic. I suppose interim features are not necessarily semantic, but they lead to a feature of sufficient abstraction and relation to things that we care about. At some point, they become semantic.
Yeah, like if we think of lottery, maybe these big networks, they don't find all the features that might exist. And then lottery gets are like, well, here's the connection. Like, good job, you found all these features. Here are the features you actually need. Like, if we're thinking of it as just connecting features sequentially,
Yeah, and then the question is which ones? I mean, basically the model of the world he's putting up here is that you have a world model in your head, that's this sparse factor graph, and you basically only ever update a small part of that factor graph, and because you have this assumption that of localized change and so on. And that's what you said before, where that ties in, right? Maybe you have the dense computation, but only on a sparse part, on a small part of that factor graph at a time. So you kind of focus your attention on that. So like if you learn something new about physics, you're not going to update your entire, you're not going to question your knowledge that you have about your tax form, right? It's because you've learned something new about quantum physics, like, oh, that's interesting. You're not going to revise everything. And maybe that connects to how I wash my back in the morning, or, you know, that this notion of localized change, and also localized change in this factor graph, and the way you learn is you update a very small part. Still leaves out the question of how do you connect new things. But maybe we're terrible at that as humans. Maybe that's but I think the model is incomplete. I just want to point out that this graph isn't really sparse. I mean, it's just like top left, everything's connected to everything.
I think his system too doesn't include drawing pretty slide decks either.
But it's strange. Every single thing is just like 3 pixels over the boxes aren't the same size. It's like, this is what happens when you export like a PowerPoint and then you upload it to Google Slides and then you download it again and you convert it to a PDF.
It's hilarious. I think he's built this in Microsoft Paint.
Or it could be like a package, like these LaTeX packages that build graphs for you.
No, they're
you
great.
Can't really control how they. You just say this should be connected, and they somehow figure out how to. Yeah, but ultimately, I mean, I get what he's saying, and it's pretty smart, right? And it's a good model. I disagree with some parts of that model. I question also the ability for us to learn this with the techniques we have right now. I'm not sure, and mostly I'm not sure how that connects to consciousness.
I would agree with that. I think just to sum up, I've found it a bit difficult to wrestle with this. I think he's got some very interesting ideas. Clearly, he started off the presentation by saying we've gone a long way with consciousness, especially in the neuroscience world. Consciousness is no longer a dirty word, and we should take all of the information that we've learned from the neuroscience world and we should formalize it and we should build it into our machine learning models.
Yeah, no, I'm surprised that agency is just black and not red, if that has any meaning. One of my favorite papers of his is Experience Grounds Language, and I really like that idea, how the agency, like back to the idea that like this shit, like I verbalize my knowledge because there's a reason to do so. Like I think agency also, I would have liked to have seen more.
What I really loved was the beginning of his presentation, where he was using the Daniel Kahneman formalism and talking about the dichotomy between system 1 and 2 and how system 1 knowledge can't be verbalized. And a lot of that stuff has given me a very useful framework to think about AI systems in general and interpretability and how we should talk about the capabilities given this framework. I think that was very useful.
Yeah, I agree. But I'm also convinced that a system like that, with these kind of systems, that we can just approximate system 2 with system 1. Like the idea of how the skateboarder who skateboards all day, he can just system 1 it, whereas I would need to plan it out. So I think that with a sufficiently powerful model and data, you could just, I think that any system, most of the system 2 stuff we think about could be approximated in a intuitive kind of way, just a forward pass way.
That's interesting.
With Yannick's example with AlphaGo with the Monte Carlo tree search, I think that's just the perfect example of system 2, system 1. So the Monte Carlo tree search is like a planning way to get a better action. But the way they do AlphaGo 0 is they distill the Monte Carlo tree search's actions into the first neural network. So this is the intuitive system 1 thing. And then this distribution would be like, I mean, it's still back into the same thing, but this would be the system 2 result. And I think they do, put the Monte Carlo tree search into the policy pretty well.
Ooh. Yes, I agree. Yeah, that's. I mean, the interface of system 2 to system 1 I believe, is more like a guided search than it is maybe this factor graph thing. But maybe there's a way to combine the two. Like this search will be over a factor graph.
Cool. Well, I was going to tell, I think that okay, so first there's this idea of measuring types of generalization. Then I like the neural module networks. I want to talk about that. The idea of I really like this thing about how if you're going to detect my hand gesture, it's better to first crop out my hand and then do that. So that, composing these things you can do. I like that a lot. Then the sparse representations, he didn't really talk about meta learning, where you take one task and see what features or the variables that connect the tasks, even though I think that's something that he studies a lot. And then I like that's the last one. And then I like agency and grounding, although he didn't talk about that either.
I hope that you enjoyed Bengio's talk as much as we did. And thank you so much for being with us, and we will see you next week.